A random variable is discrete if there is a countable set of values, ai's, such that the probability that x equals ai summed over all I adds up to 1. So a random variable x is discrete if there is such a countable set of values that it takes. We sometimes call these values atoms that the random variable takes on. The simplest example of a discrete distribution is the Bernoulli p, which is a binary random variable which takes on the values 0 and 1. The Bernoulli p random variable it takes the value 1 with probability p and the value 0 with probability 1 minus p. So the PMF px of k is equal to p if k equals 1, 1 minus p if k equals 0, and 0 otherwise. Okay, we use this binary distribution very, very often in our probability models. Another example that is related to the independent trials experiment is the geometric distribution with parameter p. Remember when we did a sequence of independent trials with success probability p in each trial, the total number of attempts until we get a success, including the attempt on which we have a success, has the geometric distribution such that the probability that the number of trials is k is p times 1 minus p to the k minus 1, because we're looking for k minus 1 failures followed by a success. So here k can be 1 up to infinity, integers from 1 up to infinity. This is so basically the PMF is 0 for all other values of k, for negative values of k, and k equals 0. All right. Now another very common discrete distribution that is related to the independent trials experiment is the binomial distribution. This is now the total, essentially this comes from counting the total number of successes in a given number of trials. So the binomial distribution has two parameters, n and p. And essentially the random variable x is a total number of successful attempts in a total of n trials, where the success probability is p in each trial, and successive attempts are independent of each other. So px of k is equal to n choose k, p to the k, 1 minus p to the n minus k. And this is for k between 0 and n, integer values between 0 and n. All right, so the Bernoulli, the geometric, and the binomial. And they're all simple discrete distributions. On the right, you see a plot of the binomial distribution where p equals 0.25 and n equals 7 on the top plot. And on the bottom plot, again, p equals 0.25, but n equals 40. You see how when the number of trials is increased, the distribution becomes smoother. There is a way to further smoothen this distribution, and in fact, there's a related discrete probability mass function which is not limited to a finite set where the PMF has values, takes values up to infinity. And that is the Poisson PMF. So let's write the PMF down. A random variable x has the Poisson PMF with parameter lambda. Note that it has just one parameter lambda. That is essentially the rate of arrivals, and we will talk more about this when we talk about the Poisson process later on. When the PMF is lambda to the k, e to the minus lambda over k factorial for k integers, positive integers union 0, basically k bigger than or equal to 0. Okay, now actually the Poisson distribution can be obtained as a certain limit of the binomial distribution. So when we take a binomial PMF and let n go to infinity, the number of attempts go to infinity, whereas at the same time the p, the success probability, goes to 0 as lambda over n, where lambda is fixed and p goes to 0 like lambda over n. In that case, and we could talk about it perhaps later when we talk about the Poisson process, that the binomial distribution approaches a Poisson distribution.